welcome everyone to my talk, and my name is Bolun, and I'm here to talk about deep learning and in particular transfer learning. So this work is a collaboration with my colleagues and advisors from UC Santa Barbara, U Chicago, and also Virginia Tech. Right, so deep learning has shown some really impressive improvements in the past few years. We have self-driving cars, we have very good face recognition models, we have language translation models. But all of those are only possible because of data, because we have large labeled data sets. I'll give you one example. So ImageNet. So this is a very popular benchmark test in the vision domain. And the data set used to train all models for ImageNet contains over 14 million images right now. So this is the amount of data we need to train high quality deep learning models. So as you can imagine, if we want wider adoption of deep learning, if we want everyone, normal users and small companies, to also use deep learning in their own products, they also need to collect this amount of data. And as we all know, this is an extremely hard task. So to overcome this data requirement of deep learning, we have a very popular solution called transfer learning. So this is how transfer learning works. So if you're a company with very limited training data, you need to turn to those who have access to large data sets and have the ability to train high quality models. And let's say Google. And if they open source any models for similar tasks, what you can do is you can grab those models and adapt these models using your own data sets. And then you will have a very high quality model that is specifically designed for your own task. So this process is called transfer learning. So essentially what we're doing here is we're transferring the knowledge from those high quality models and adapt them to our own task. So the high quality model we borrow from large companies is called the teacher model. And the model we train ourselves is called the student model. So we're transferring the knowledge from teacher to student. So this is the only solution we have so far when we need to train a high-quality deep learning model with limited data. So this is why large companies like Google, Microsoft, and Facebook, they're open sourcing their models to the public so everyone can build their own student models on top of those high-quality teachers. And this is also recommended by those large companies as sort of go-to solution if you want to train a model with limited data. So before I go into any detail about transfer learning, I just want to make sure that everyone understands the basics about deep learning. So deep learning model is this layers of neurons, and they are stacked on top of each other. So every single neuron represents a feature of the input. And then when we feed this image into the model, for example, this cute image of dog, there will be many neurons are activated by this image. And then they will fire more neurons in the next layer and the next layer, and eventually the last layer will tell you this is a dog. Right? So when it comes to transfer learning, and let's say we have a teacher model with n layers, so the last layer is always a classification layer. And this is specific to the teacher task. So we'll just put this one aside. And then what we do is we transfer the remaining n-1 layers to the student. So the intuition here is that the output of those n-1 layers are extremely high quality features. And we can directly reuse those features and build a very simple classification layers on top of it. So we built this layer using the student data set. So this model is specifically built for your own student task. And this is how we build a student. And in general, you can directly transfer the first k layers. And in this case, we use the first n-1 layers. So to show you how effective transfer learning is, this is one example of a face recognition task. So we want to recognize faces of 65 different people. And the data set is extremely small. We only have 10 images per person. And what we do here is we transfer from a teacher model called VGG face. So this model is trained on an extremely large data set with more than 2,600 people and more than 900 images per person. So if we do the training without transfer learning, we'll get around 1% accuracy. So this model is basically useless. But with transfer learning, we can get as high as 93% accuracy. So this just shows you how effective transfer learning is. So what we want to ask in this project is whether transfer learning is safe, whether transfer learning can produce robust student models or not. And what we find is that transfer learning doesn't have a lot of diversity. And because there is only a limited number of large data sets out there, so when it comes to transfer learning, users will have very limited choices of teacher model. So a lot of companies will be building their student models on top of the same teacher. And it also means the attacker will get the same copy of teacher model. And this is the same model you use to build your students. And what we found is that in this paper is that this information about the teacher can really help the attacker launch attacks on all student models out there. All right, so in this talk, I will tell you how this attack works, and I'll show you how this impacts real deep learning services, and I'll also show you some defense solutions. All right, so first off, a little background about adversarial attack on deep learning. So adversarial attack on deep learning is mostly about trying to misclassify inputs by adding some carefully engineered perturbation to the inputs. So for example, here we have an image of Angelina Jolie, and by adding some little modification to the image, the model will misclassify that as Adam Sandler. So the modification we add to the image is typically very small, so human cannot see it. And based on the attack model we have Whitebox attack. So the Whitebox attack assumes we have full access to the model internals. So that includes the architecture, all the weights in the model. And basically what you do is you can do all the computation offline, and you can find the optimal perturbation you need to launch the attack. But the problem about that is this assumption of full access is not really practical. So in a lot of cases, the service provider will not just give away its internal design of the model to attackers. So this is not really a practical assumption. So that's why we have Blackbox attack. So Blackbox attack assumes we have no access to such information. So then what you do instead is you can repeatedly query the victim model. You can do this to either reverse engineer how the model works inside, or you can test some intermediate perturbations you have and try to improve on top of it. And the problem about this is that in a lot of cases, you need tons of queries to do the natural attack. And this repeated query behavior itself can be very easily detected. So you can see both models have their own problems. That's why we are proposing a new adversarial attack. And this is specifically targeting the transfer learning scenario. So our attack model is a little different. So we assume the teacher model is a white box. So we know everything about the teacher. But the student, on the other hand, is a black box. So we don't know all the detail about the student model. And this is the default access model of transfer learning right now, because all these popular deep learning services are making their teacher models public, and they're making it public to everyone, and that includes the attacker. So you can literally go to Google's website and search for their teacher models and download it to your laptop. So you know everything about the teacher. But student models are typically trained offline using their proprietary datasets. So whatever modification happened during transfer learning are totally hidden from the attacker. So how do we attack the student without knowing its weights? So let's say here we want to misclassify this cat, which is in the bottom, into a dog. So as I said before, deep neural net is this stacked layers, right? So every single layer only sees outputs from previous layers. So then our attack is trying to mimic the neuron values of the target image at layer K. So here I will show you two vectors. So the task is trying to make these two neuron vectors match each other. So if we can do that, when these two neuron vectors are passed on to the next layer, the outputs will also be the same, because same input neuron vectors, same layer, same output. And this is the same for the next layer as well. So, and eventually, the model will produce the same prediction results for two images. So this is how the attack works. We try to mimic the neuron values in one of the middle layers. And because the first K layers are not updated during transfer learning, so we can do all the computation we need on the teacher model to find the perturbation we need. And the way we compute the perturbation is a very standard optimization technique, and this is also used in some prior work as well. So the goal here is try to mimic the hidden layer representation. And we also have a constraint, which is we want the perturbation to be indistinguishable by humans. We don't want a human to see this perturbation. So that's why the main objective here is try to minimize the distance between two representations. And we use a very simple L2 distance to measure that. And the constraint term is trying to control the amount of modification we add to the image. So here we use a metric called DSSIM to measure the amount of perturbation. So DSSIM is an objective measure for image distortion. This is often used in the vision domain. So this constraint term will make sure that the amount is minimum and the human cannot see it. And we also have a variable P budget here, and this is a knob that the attacker can tune to control how much perturbation he wants to add. So to see how this attack works, we tested on student models we train ourselves. And here we mainly focus on targeted attack. So we want targeted misclassification. We randomly selected 1,000 source and target image pairs, and we calculate the attack success rate. So this is the percentage of images being classified into the target. So this is one example of a face recognition task. So we achieved higher than 92% success rate. So if we switch to a different application scenario, for example, iris recognition, the attack also works. So we achieve higher than 95% success rate. And also notice that this is the attack success rate of one single try. So if this one doesn't work, the attacker can simply switch to a different image and he'll probably get successful. Right. So we also want to see whether this attack works in the wild. And the first problem we need to solve is, given a student model, how do we determine which teacher model was used during transfer learning? So I don't have time to cover all the details here, but essentially what we do is we propose a technique called fingerpainting. So we can craft this fingerprint input for every single teacher candidate out there. And then we query the student model using those inputs. And based on the prediction results, we can see which teacher model is used. So we also want to see whether this attack works on real students trained by real deep learning services. But because of ethical reasons, we can't just go ahead and attack those real students. So instead, what we do is we train student models ourselves. And we do that by following the exact tutorials and the exact teacher models provided by those services. So we tested on Google Cloud ML, Microsoft CNTK, and PyTorch. And PyTorch is developed by Facebook. So in all cases, the fingerprinting attack works, and we achieved higher than 88% success rate. Right, so now let's talk about how to patch up those student models. So the intuition is extremely straightforward. So the attack is trying to mimic the output of layer K in the teacher model. So the defense should be modifying the student so its internal representations doesn't match that in the teacher anymore. So then the attack will be mimicking the wrong internal representations, and the attack will fail fundamentally. So this is how the defense works. We also have some other requirements for defense. First, we want the modification to the student to be unpredictable by the attacker. So there's no way for the attacker to fight back. There's no countermeasure. And then we also don't want to sacrifice the model performance during the process. So what we do is we modify the objective function used in transfer learning. And this new objective function will make sure that the student is sufficiently different from the teacher. So if you use this, if you do transfer learning using this objective function, the trained student model will be robust. And for other student models that are already trained and already vulnerable, what you can do is you can fine-tune those students for a few epochs using the new objective function. So this will make those student models robust. So the new objective function looks like this. The main objective is still trying to minimize the cross entropy. So we still want to keep the same level of model performance. And we have a new constraint term here. And this constraint term will make sure that there is enough difference between the student and teacher. So this turns out to be really effective. And in the two examples I showed you before, we managed to reduce the attack success rate from above 90% down to 30% and 12%. And also, this defense has very small impact on the model accuracy. So this shows that we really can make the student robust without sacrificing the performance. And before I finish my talk, I also want to point out that we already disclosed all our findings to Google, Microsoft, and Facebook, and they're actively looking into the matter. And I don't really have enough time to talk about all the interesting details in the paper, but I strongly encourage you to read the paper if you're interested. For example, we have a detailed measurement about how different transfer learning approaches affected the attack performance. And we also have the full description of how the fingerprinting attack works. And also our code and pre-trained models and datasets are all available on GitHub, so feel free to try it out. And with that, I'll conclude my talk. I'm happy to take questions.
So we have good time for questions.
Hi, Yang Zhang from CISPA. So your attack is focused on the adversary examples. So have you ever actually tried to generalize your attack to other kind of attacks against machine learning models, such as membership inference or model inversion or model stealing?
You mean other domains? Or
yeah, other kind of attacks. Because the general thing is transfer learning is actually the general paradigm, but actually...
Oh, other type of attack. So this work is mainly focused on adversarial attack in deep learning. So we haven't looked into other types of attack yet. So, but that will be a very interesting follow-up work.
Hi, Michael Clifford, Nobles. So when we look into data sets that we could apply to problems for machine learning, we find that there aren't publicly available data sets that are useful for a lot of security problems. So rather than attacking the data set, if you want to train on something for a security problem, we find that there's not really a lot out there. Have you found anything that might be useful for security-related machine learning problems?
So I have not, so this paper, all the data sets used in this paper are mainly about image classification. So I'm really sorry that we didn't find a lot of security-related data sets out there, but I'll definitely look it up.
Hi, I'm from the University of South Florida. I have a question about what about the defense you used for the distance between the regional and the crafted samples. How did you decide the distance, this kind of metric? Do you have any solutions for how to choose the distance? Right.
So the question is about this parameter we used for defense. So that parameter I showed you in the equation, that one controls how much difference you want between the student and teacher. So in general, the larger the better, means more secure and robust.
But when you choose the larger, then maybe the transfer learning, the first process, the accuracy will be decreased, I think.
Yeah, right.
Right.
So I was about to say.
You will have a higher accuracy of the transfer learning, but on the other side, it might be like decreasing.
Right. So the general trend we saw was when you use larger threshold, you will have more robust models. It will have a little bit more impact on the model classification. Yeah. But as I showed you before, this impact is really small comparing to other defense methods we tested.
So you just, in your paper, you just choose them randomly, or?
So in our paper, we tested different thresholds. And in practice, when the user is actually trying to pick one, what they can do is they can set the tolerance for model performance drop they can tolerate, and try to increase the threshold until they hit that point. So then they will have a guaranteed performance model, and then they will have more robust models.
Okay, thank you.
Oh, hi. My name is Sun Zhang from Johns Hopkins University. I have a question about the feature extractor you have used for transfer learning. So what if we fine-tune the feature extractor? So for example, when you do fine-tuning, you currently only fine-tune the last several layers. So how about you fine-tune the entire model? What will happen?
Right. So the question is about what if you don't just fine-tune the last layer, but
yes.
instead the full model. So we actually analyzed that transfer learning approach in the paper. So what we found is that this will make the model more robust against this type of attack because you're modifying the model more, so it's more different from the teacher. But the difficulty here is that this approach also requires a lot more data to train the model because you're not only training one layer, but the entire model instead. So this will put a lot more requirements on the data and the computation resource for the user.
Okay, thank you.
Any other questions? I have one. So, did you consider an adaptive adversary when building the neuron-distance defense?
Right. So we thought about countermeasures from the attacker side. And I mentioned, this is one smaller point I mentioned before, is that when you do defense, you're modifying the student using your student data set. So when you're modifying a student, the attacker cannot know what kind of modification you do to the entire model. So this part is unpredictable. So that means the attacker cannot reproduce the process. And so it's really hard to do countermeasure.
Okay. Let's thank the speaker once again.